In this talk, I will explain how the so-called Elm architecture for purely functional graphical user interfaces can be viewed from the type theory and functional programming point of view. And I will explain how to, in particular, combine larger Elm programs from components motivated by the types. First, I will give an overview of how graphical user interfaces are understood from the purely functional point of view. Usually, graphical user interfaces are implemented imperatively. Even frameworks such as React, that is inspired by purely functional programming point of view, still uses imperative code, and most frameworks are not purely functional in this sense. Now, if you approach graphical interfaces from that point of view, you have to then describe them as asynchronous streams of values. And it turns out that those streams of values have to be recursively defined. So that's a pretty complicated description. I will show how that works. In order to have passable performance, one uses a runtime engine that does a lot of tricks, such as virtual layout and caching, and actually, it, of course, uses imperative updates rather than creating huge data structures in memory. It modifies visual elements in place and so on, but all of that is transparent to the programmer. It is invisible to the programmer. The programmer writes code in a purely functional way. So that is how graphical user interfaces are implemented. Now, Elm architecture is a way of simplifying this entire construction. And the Elm architecture hides asynchronous streams and recursion from the user. The user's code is non-recursive. It has no side effects. It is a purely functional code that can be described as a model view event update. So model view event update, I will explain how that works in detail. Essentially, there are types for model, for view, and view is a type constructor, parameterized by event type. So there's a specific type of event. I will explain why it is reasonable that the view is parameterized by an event type. And then essentially, a program in the Elm architecture is a value of a certain type. So it's a purely functional view of graphical user interfaces is a value of this type I call TEA for the Elm architecture. It's written here in the Scala syntax, in Haskell syntax, and in the mathematical syntax that I'm using in my books, in my book on functional programming. Essentially, it's a very simplified view. So if you look at the Elm language, it will be more complicated than this, but I will explain that it is actually equivalent. I'm omitting here the initial value of the model because it's not very essential. Now, I will explain how you run this program. So to run this program, you use an interpreter, which makes a single model update. So a single step of updating the previous model value to the new model value. And then, because you have this function from model to view, you compute a new view. So in this way, you run the Elm program. So it is a known issue in the Elm architecture that it tends to be quite monolithic. So in the sense that the entire program, all its elements need to be contained in a single view. All possible events need to be described by a single type of events, and all possible values that you need to store need to be in a single large value for the model type. So it is not modular, in other words. The entire program is a monolithic value of this single type, and this type cannot be easily split into parts, into smaller m's and smaller e's that you can kind of combine. This type is coupled in such a way that it's not easy to split. So this is a problem. There are some solutions for this problem, but I will just approach it from the point of view of functional programming and types. So how can we combine two graphical user interface components like these? This should be 2 here. How do we combine these into a larger component of the same kind? And I will show 3 ways of combining. One is a non-interacting join of 2 components. So that means they are just run side by side. There's no interaction between them whatsoever. And that's pretty easy to describe in terms of types. And then I can show how to obtain the value of this type for the large program, given 2 values of this type from smaller programs. Now, I will then show how to modify this combinator to describe that one component can consume an event from another component, or more than one event from another component. So for example, imagine you have a button and you have a large window, and if you press the button, the large window is closed. So that means one component consumes events from another component. And then I will modify that to obtain a nested view, so that one component is has a view that is nested within another component. So I will explain what needs to be done to describe that in terms of types. Now, I begin by overview of a GUI as reactive streams. So the usual way that graphical user interfaces are programmed is imperative. That means you have destructive update of the visual components as well as some data in memory that is being modified all the time as you run and interact with the program. In functional programming, instead of modifying, you copy, and you create a new copy of the same data, and then you modify that. So you don't modify the initial copy. So that's how you can view the main approach of functional programming. So you, for example, you don't mutate a value, you create a new value, which means that if we describe graphical user interfaces in purely functional program, it means that we will have copies of all the data as it is being modified. So we'll have, let's say, initial data at some initial time, then it's modified. We'll have another copy of pretty much all that data with some things modified, and so on. So we have a stream, in a sense, which is created at runtime every time that the user modifies some element in the user interface so that the data needs to be changed. We need to imagine that we create a new value of this model type. So we introduce type M, and the value M0, M1, M2. Let me write these values perhaps as lowercase. So all these values, mi, 0, 1, etc., will have to be created in a stream. So this will be a stream of this potentially infinite number of different values. All of these values will be of type n. Each time that the user interface is changed, each time a button is pressed or a new list is displayed or something, we have a new visual layout and visual content. So there is this window with sub-windows and so on, and a complicated layout. And all that needs to be described by some value. So let's describe this by a value of type v, v for view. So then each time that the user changes something, it's not only that the model changes, but also the view must change. So then we'll have different views with different scroll positions and so on and so on. So you type in something into a form, then that changes the view, that changes the model and so on. So the type V can describe all possible views that you will ever see for this program. And so it's a pretty large type. It could be a very large tree. Usually in today's graphical interfaces, the layout is just a tree of nested rectangles with attributes. So for simplicity, we can say that V is a tree-like, so it's a rose tree where each node can have any number of branches, finite but not fixed number of branches. It's like a rose tree where you have rectangles at each node. So you have a rectangle and then it has some more rectangles, and then each of them might have more, might have nothing, but it might have more and more. So there's this type V, which we will not write explicitly. It depends on a specific implementation, operating system, graphical toolkit, and so on. But it's always of this sort. Like in the browsers is the HTML document, which is a tree of tags and so on. So it's the same kind of idea. And the data inside this V will be shown. That's the point that the system will take the value of type V and somehow display that value using graphics. And so we will have initial view, then the next view, then the next view. So all of these lowercase v's, they're going to be values of type V. And we will have, again, a stream of potentially infinite number of them created at runtime as the user interacts with the program. Finally, how does the user interact with the program? We need to describe that somehow. So each possible way that the user interacts with the program, for example, pressing a button, dragging the mouse, whatever, typing text, talking into the microphone, making images with a camera, and so on and so on, even downloading from the internet, all that is interaction. And we need a type that describes all possible interactions. So values of this type will describe events of interaction. For example, we received bytes from some 50 bytes from the internet in that channel of communication. We received these characters from the user through the keyboard, and so on. So all of these values need to be described as values of a certain type. So let's call this type E for event. And so let's look at this diagram here. So we are evolving, time goes to the right. We are evolving our application as we are interacting with it. Each time, so the next step happens because some event of interaction happens. Usually, graphical user interface programs don't do anything on their own. They sit and wait until something happens. They wait until some event happens. And when that event happens, they make updates, make changes. So here, therefore, we expect that there's going to be some event E0. And because this event happened, we transition to the next state. And then some event E1 happened. Because of this event, we transition to the next state, and so on. So this is how we imagine that this works. Now, where do we get these events E1, E0, and so on? We get them from different sources, from directly input from the user clicking on the view. So there is actually a dependency. So the events that are possible at any given time depend on what is shown on the screen. So they depend on the view. And also the view depends on the model, because the view shows, well, it's a tree that displays some layout, but the content of this layout is a function of the model value. So now we have a situation where we have three streams of values. The stream M, M0, M1, M2. The stream of views, V0, V1, V2. The stream of events, E0, E1, E2. And what we say is that the views are a function of the model, and the events are a function of the view. But also the model is updated when events come. So the model is a function of the events. Now we can write down these functions explicitly. For example, usually one says that the view at any given time is a function only of the model at the same time. And that means there is a function, let's call this function display, which is from type M to type V. And we just apply this function to each value of type M here. We apply and we get the view. So this stream is just equal to that stream map display. This stream is more difficult to relate to this one because of various reasons. One reason is that we don't know which event will happen. So this view, for example, could contain some buttons, but we don't know which one of them will be pressed. Or maybe none of them will be pressed, instead some other event will happen that has nothing to do with these buttons. Such as, for example, the user decides to turn their iPhone sideways, and then there's an event that causes the entire view to be drawn in a new way, the entire layout to be changed. And that also could change the model. And so we don't know which events come. So that is not a function. So this stream is not, strictly speaking, a function of this or this. But nevertheless, it depends on those things. It depends on the view, because you cannot press a button if this button is not in the view, for example. And so there is some kind of dependency. But this dependency is not so easy to express as a function. It's not a function. So this dependency will be somehow realized by the runtime engine. And so we cannot really write this as a function in a purely functional paradigm. Now, the last step we can write as a function. We can write an update function, which takes an event old model and produces a new model. So then we can say, well, the model stream is a scan of this update function, given an initial value of the model and given the stream of events. Now, the initial value of the model can be presumed to be fixed once and for all. So let's not worry about that. So this is the way that we define graphical user interfaces in the purely functional paradigm. Notice that this is a definition of 3 streams, potentially infinite, with recursion. So because one of them is defined through the other, this is a function of this. This is somehow a function of this through the runtime. And this is a function of that. So it's a recursive definition. These streams need to be asynchronous. They cannot be computed in advance because the events come at unpredictable times. So we have to wait until event comes, and then the event comes and we can produce the next elements of these streams. So computing these streams needs asynchronous implementation. From the point of view of functional programming, this is not very important. Important is that we have these data structures that need to be computed. And the important part, the difficult part, is that this is not a function from view to event. Somehow there is some kind of effect going on here that is not just waiting for the new value to be computed, because it's non-deterministic what will happen. And so really we don't, so we can put this effect in terms of functional programming. It's fine, we can just produce some description of it. And let's say this is going to be user does of event. So that is going to be the value. Instead of just E, it's going to be the type constructor user does E. And this type constructor describes the asynchronous non-deterministic choice of a value of type E. And then we can make a stream where each next element is wrapped under this user does. So that's just an effectful stream. In functional programming, this is a well-known data structure. And then we will have maybe a monad of this kind of stream and so on. And so this is getting quite complicated. If you want to write this, and still you won't be able to write this as a function because this needs to wait for the system to do something. So this will have to be some magic type that the runtime engine will work with. So to summarize, we are not really able to describe user interfaces in a purely functional way completely because of these complications. And even if we left those parts for the engine, the description would be quite complicated. We are dealing with some complicated effectful streams, data structures with complicated definitions. So the point of the Elm architecture is to simplify all this. How do we simplify this? Now, we say that we're not going to describe this stream as a data structure. We're not going to describe stream of models directly as a value in our program. We're going to describe a single step of update. So how do we describe a single step of update? We have a previous value of type M. Let's call it M1. We compute a view out of it. Let's call it V1. Now, we will make this view contain the possible event values that it could generate. So that is another design choice, so that this view actually will contain not just the rectangle coordinates and attributes, colors, and so on. It will also contain special values of type E. That, for example, each button will contain a value of type E that corresponds to the event of pressing just that button. So that means that we have a tree. So V will have this sort of data structure where we have a tree with nested rectangles, which are graphically going to be nested like this, perhaps, something like that, and so on. But if this is a button, like this is a button, then this button will also, so it will be some rectangle, but also it will contain some value, let's call it E1. So this node of the tree will carry additionally a value of type E. And in such a way that the runtime system will recognize that, and will recognize that E1 is a value that corresponds to pressing the button in this rectangle. If this rectangle is the button. So it means that our type V actually carries values of some event type. Now, this event type is completely extraneous to the view. It is kind of contained by it. So the most natural way of looking at this V is as a container of values of type E. And so for this reason, we say we're just parameterizing. We make V a type constructor. So V is a type constructor parameterized by the event type E. We will be able to use that with whatever event type, because the event type is not part of the data structure dictated by the graphical toolkit. It's something we put on top of it. And since we put on top of it, it's natural to make it a type parameter so that we can put arbitrary values on top of it in the same way. And so each button is additionally labeled by a certain value of type E. Each scroll bar, each input field, everything is labeled additionally with values of type. And so we will provide this function, which is display, which will now have the type signature M to V of E. I'm writing it in kind of Scala syntax, but this is just to be more clear to myself. Additionally, you need to specify what happens when the event comes. So you have a function which is update EMM. So that's all you do, and you do not describe in your program the infinite streams that result from running this. You do not have recursion, you do not have effects. Actually, your program is just these two functions. These are pure functions. They have no side effects. They compute values. So V is a virtual layout. It doesn't have to be, but of course, if it isn't, then you're going to be extremely inefficient. In web applications, this is called virtual DOM. This is just their jargon. It's a virtual layout. It's a data structure that represents the layout and all the attributes that you need. And then the runtime engine will draw all this. And the runtime engine knows how to extract events out of these elements. And since each element that is capable of generating events is labeled by a certain value of type E, then the runtime engine will be able to extract those values of type E. And so to summarize, the Elm program is a value of this type TEA, which is M to V of E, comma, E to M to M. And to run this program, all you need is some kind of rendering engine that will efficiently render values of type V, so it will draw them in efficient way, so that if the value of type V changes a little bit from the last time you drew it, and you don't redraw everything from scratch, you just change what needs to be changed. So that is the usual optimization that is needed in this kind of approach. And then essentially, as I described, the values of type E are tacked on the graphical elements. And so the runtime engine will be able to extract those values from the view to see what was actually pressed, which scroll bar or button or text field or whatever actually created events from the user right now. And so this functionality is equivalent to having a function of this type that extracts a specific value of type E from a view. In other words, it waits until something happens, and when that happens, then it knows how to find which component generated a signal and what value E corresponds to that signal. Now, the actual value E could have parameters from the signal, so it's not just a single number. E is not a numeric type. E is usually an algebraic data type with a lot of data. That, for example, when you describe a text input, then a specific value of type E will contain the text that is typed in. You could even have timestamps in each keystroke and so on. So depending on what needs to be done, this type E could be quite complicated and rich. So the interpreter needs this function. It needs a function of type TEA or value of type TEA. And then it produces the next value of model and the next view from the previous one. So it's a single step interpreter. And that's pretty easy to see how that should work. So if you have a value of type M to V of E, if you have E to M to M, if you have V of E to E, then you can substitute this V of E in here. You get M to E. And then you can swap the curried arguments in here, and so that it's M to E to M. And then you have M to E. So given M, you get an E. You substitute that E in there, and then you get your final value. So we can write code of the interpreter, which will take parameters. Display. So this, I call this function get event. Display, update, get event. Now this will be of type M to M, as we need. So this will be a single update step, and the code run of display, update, get event M will be just you display M, so that you get a view, and you extract the events from this view, you get an event. Then you run the update function. So update is E to M to M. Now this is, of course, a very rough outline of what is going on there, but that is essentially the only way that you could implement a function of this type signature. Now, this is a very interesting thing because it means we have a very simple way of characterizing arbitrary graphical interfaces in terms of values. And then there's a single way of running those programs. Now, let me show you an interesting simplification that you can do using type theory. Once you accept that this program has the type M to V of E, EMM. Now we can simplify this type by hiding the event type. Actually, the event type is can be hidden. It does not necessarily have to be explicit. And this might actually help reason about the program in some ways, but not necessarily to write code. So when you write code, of course, event types are very, very important. Let's rewrite this like M to something. So let's swap these two arguments again. And we have V of M to V of E, comma, M to E to M. So that is equivalent. Now let's see, this is a pair of functions from M to something. So we have a pair of functions from M to something. This is equivalent to a single function from M to the product, to the pair of those things. Now this, you can pretend that the type E is existentially quantified, because you might not care what it is. So if you write exists E, V of E times E to M, that is a Coyoneda lemma that is equivalent to V of M. So then we get M to V of M. So now this is a very interesting simplification because it says that you can simplify the Elm program to just having a single type model and the view type constructor, as long as V is a functor, which it will be, according to our idea that the event values are just decorations on top of some rectangle attributes. So this is a much simpler type to reason about, and we can try to use that in formal reasoning. So essentially, this is even easier to run because you take initial M, you compute this V, then you extract the events from it. So the same function which extracted events, it is parametric in the event type, so it will work in exactly the same way to extract M values. So then you directly extract the next model value from it. So that simplifies very much the runtime. So you could say, well, I have performed a symbolic simplification and symbolic optimization of my program to an equivalent simpler type. So now let me talk about combining two Elm programs into a larger Elm program. The simplest combinator is when the two graphical user interfaces are side by side and they're not interacting. So that means that the view, let's see, we have first program M1 to V of M1, M2 to V of M2. And we are just combining them. So the model M is M1 times M2. It's just a pair of M1 and 2. Let me maybe make notation more programming-like. And the view is just the product of two views. So the view V of M is V1 of M1 times V2 of M2. Now, times is just a comma in the programming language notation. Now, what we need is actually a V of M and not of M1 and M2 separately. So we can always, when we have a function from M to something, now this is not quite what we want. What we want is a function from M to some V of M. Right, so we should be writing it like this. And all we need to do is that M1 goes into V1 of M1. And then you use functors map to map that into V1 of M1 times M2. So let me write it like this. M1, M2. First, we map this into V1 of M1, comma, V2 of M2. Then we map this into V1 of M1 times M2. This into V2, sorry, this is again comma, V2 M1 comma M2. Because we can just use functors map and insert a fixed constant value M2 into here. And so this is then what we need. So this is V of M. So in this way, now it is simpler to do it like this than to go through the effect, through the event type, but it is equivalent since it is an equivalent picture. So this is not very interesting, obviously. What we need is that one view consumes events from the other. What does it mean? Now, in this case, it means, let's go back to the event picture. So we have first display function, second display function. We have the first update function and the second update function. Now what we want is that the first component produces some event and the second component consumes it. How can we do that? What does it mean that it consumes it? When an event E1 happens, maybe so usually usually the event type is a co-product of many different possible events. And usually it's just a co-product of all possible interaction events. So when a specific part of this co-product happens, then we need to map this into E2. Otherwise, we cannot map it into E2. So E2 are events that the second component understands. And so some of these events need to come from here. So how does it work? Well, the easiest way is to say we have a function, which is send maybe. And this function will take an event from the first component and return a maybe of the event of the second component. And so if you do that, so if you have this function, then the runtime can apply this function whenever the first component generates the event. It can run this event in the first component, just as before, do the update, but also apply this function. And if this function returns a non-empty value of type E2, then pretend that event E2 happened. Even though event E2 did not actually happen here. So that is how you could do coupling of the events. And you could also send events back from E2 to E1. So it's all you have to do is to have another function like that, send to 1. So in this way, it is clear that any number of components could interact. So in order to describe this interaction, the user first implements individual components as if they're not interacting. And then the user implements these functions. The runtime engine should understand that the presence of these functions means that the components are coupled and they have to consume events from each other sometimes. Now, how to do this in a programming language, that is a separate question. It's a technical implementation. Clearly, you need to specify a number of those functions from event types to other event types somehow when you define your program. So you can certainly implement that in a number of programming languages. And finally, let's see how we can nest views. So the usual way that components are combined in a graphical user interface is that you have here already some components, and then you need to put some other view, some graph, let's say, function. And here you would still have some stuff that you are handling, but everything here will be handled by a different component. So ideally, you will write code separately from here. So you will write first a component like this, knowing nothing about this yellow stuff. Then you write just the yellow stuff. And then somehow you need to say that a specific part of the view in the first component, so a specific part of this, corresponds to the entire view of this. So this has to be inserted in here. And whatever updates are here need to be done also need to be shown in here. So certainly we can do that only if there's some way in which we can identify what parts of V1 are the yellow ones. So there might be more than one, maybe more than one place where this happens, or maybe there are 3 copies of this. I don't know. We don't know that. So in other words, again, we have a situation where V1 needs to contain some foreign stuff. And the way of implementing this in functional programming is to add type parameters. So if you have a data structure that has its own business logic, but it can also contain some placeholders for foreign stuff that it doesn't know about. It's stuff that could be anything. Usually that's implemented by type parameters. So then you have instead of just one type parameter in the view, you have 2. Let's call that N and E. So now the N is the nested part, and the values of N are actually going to be perhaps not so clear what they must be right now, but somehow they must correspond to the yellow stuff. So let's think about how this could work, and then it will become clear what still needs to be done, because it's not going to be working like that. So suppose you begin running this program. It will run the first step, and it will draw some view here. Now this view will need to have a value of type N already. And this value of type N must be such that the second component should be able to run and draw some view. So at the very least, this N must give you some kind of model for the second component. So that gives us an idea that actually N is M2. But we don't know what value to put in there. So the value must be part of model M1. The initial value of M2 must be part of M1. Otherwise, we won't be able to compute that view V1 containing the model M2. So that means we need to change, instead of M1, we say this the old M1, and also it is M2. So, okay, so you have now this situation where your model is now a product of 2 models, and your view is parametrized. And so this function from model to view needs to take this M2. Now we will have a function from M1 prime to V1, let's call it V1 prime of M2 and E1. Note that there is no E2 in here, there's just M2, because E2 will be computed later by running this second component. So in order to compute this, you take the M2 in here and you put it into the right places. Now, how do you put it into the right places? Well, that is up to you. So you need to know what those right places are. And so at those places, instead of a view, you have this special type, which you might want to label in some way to be type safe. And then this special type will contain a model for the second component. So this is how you combine components. Now, what data do you need to specify? Well, you need to specify a function, which is M1, M2 into this V1 prime, M2, E1. So this is the function that you need to specify. It certainly could be simplified because it looks like there's a universal quantifier on M2 in here. And so this can certainly be simplified because this is by unida equivalent to M1 going to E1 prime of unit and E1. So essentially, all you need to do is to put unit types in the right places into your view instead of where M2 must be. Now, if you have more than one subcomponent, then certainly you need to put some other type, not a unit. There will be several types that you put in there. And several different views. So the idea is that the user code will just write a function like this with some labeled unit types instead of placeholder views. And the runtime will realize that this is where these different subcomponents need to be plugged in. And the runtime will change the model to be like this and put all the data in there and run. So the point is that users program should not be concerned with making this big monolithic Elm architecture out of components. That should be the work of the runtime. The user needs to specify modular functions. So this is one isolated Elm component, another isolated Elm component. And there's just a placeholder function that somehow labels by type, which is again a technical question of how best to implement this labeling and injecting of the right component in here. But that is all you need to do. So essentially you have special type, which is magic for placeholder views. And the runtime needs to recognize that and will automatically get all the right places. So in this way, you can couple components by events and by views. And so with appropriate changes to the runtime, which may be too difficult for Elm, actually, because it doesn't have so many facilities, but it could be implemented certainly as a language change. And this can be implemented pretty easily in other functional programming languages like Scala and Haskell and so on. Unfortunately, I have no time at all right now to work on this kind of project to implement, say, Scala-based modular Elm architecture based on Java Swing or Java FX or some other stuff like that. I have zero time, so I will probably take it up a few years from now when I get more time. So anyway, this is actually what I had to say. Let me add one more technical detail, which may not be very important, but the Elm architecture actually contains a lot more detail than just these two functions. And let me explain why that is not so important and why that is equivalent to what I just said. So let me say this is a full Elm program. So what is a full Elm program? According to the Elm documentation, and I admire Elm. I think it's one of the best things that ever happened to user interface development. And I encourage you to look at this and use it in your projects. So a full Elm program is a value, is a pure value, has no effects, no side effects. Elm is a purely functional language, even with no recursion, because as I showed, you don't need recursion. It's hidden in the runtime. So the full Elm program consists of the following information. So it's an M, which is model type. E is an event type. C of E is a command. S of E, subscription. V of E, it's a view. So these are the types that the user works with. And the value is the value of a following type. It's M. And then there's C of E. So there's initial command. So the command is an asynchronous effect that you can run. It has nothing to do with visual interaction. It's not a button press. It's some other effect, like for example, upload a file or something like that, or play a sound. So then there's a function from model to view. There's a function from model to I think to subscriptions. Then there is a function from event, old model, and a pair of model and command. So that's a lot of data. There are initial values specified, initial effect that will be run at the initial time. Okay. And then there is the display function. And there is a function that determines current subscriptions, which are certain kind of events that we're listening to, we allow to come. So these are still values of type E, because the type E is still required to hold all possible interaction events, including events that don't come from the user. For example, file finished downloading. It's an event that you can define. And if you subscribe to that event using this special subscription value, then it will come to your program and it will result in updates. Otherwise, if you do not have subscriptions, so a special value for no subscriptions, for example, then no such events will be coming to your program. So then you say what subscriptions you want, given this model, what view will be, and then given an event and an old model, what will be the new model, and what effects it will run then. So I claim that this is essentially the same as just M to V of E and E to M to M. Now, so how am I going to deal with effects and subscriptions? So, and initial value. Well, initial value, I admit, so one needs to have an initial value for the program. All I was showing in my talk is that I'm updating a model to a new value. So you need an initial value to start this interpreter. But what about the commands and subscriptions? So here it is quite suggestive that actually V and S can be unified in a single type constructor, product of V and S. So why not just define that and S just goes away? And C is actually similar because when a certain event comes, you update the model, and this model leads to updating a view immediately at the next step. So you can just put C as part of a view. So in other words, what I'm saying is that let's call this V prime. V prime of E equals V of E, S of E, C of E all together. So it's just that we need special provisions for the runtime to realize that some of the parts of V are actually effects or subscriptions and not visual views. But this is just technical issue. So in principle, we could get rid of this C, put it in here. And every time a new event comes, we have a new model anyway, we immediately compute a new view, and that will immediately also compute a new part of the view, which is command. And the runtime will realize that and run the effect, just as the runtime runs the view updates, which are kind of effect. So in this way, we unify all effects, including view updates, asynchronous, external commands, subscriptions to events. We unify them into a single type constructor, which is this V prime here. And then we don't need this complicated type signature. We just need this type signature. And in some cases, we can even simplify it, as I showed you, via the combinator to simplest thing ever. Model view. There's nothing else except model and view in this paradigm. Anyway, eventually I will come back to this and perhaps write a prototype, but anyone who's listening, you're welcome to do so.